Welcome to this lecture where I will tell you about unsupervised learning. In previous lectures you have seen many different supervised learning methods, and you were using those methods to predict a specific target quantity. In unsupervised learning you're doing something different. You are working with unstructured, unlabeled data, and you're trying to extract information from this dataset. So let's see with a graphical example what are the differences between these two methods. When you use supervised learning methods, you have a situation as the one you can see in the screen. So you have some data, and in this case we have labels, so some data points are triangles and others are square. And you might imagine each point has a different material. The coordinates could be the specific, the coordinates of the atoms of your material, and the label is any target quantity, as, for example, what is the most stable structure of the material. In unsupervised learning, instead, you have something different. All data are unlabeled, so each data is the same, and you're not trying to predict a quantity, but you're trying to understand how data is structured. In this lecture, I will mainly focus on clustering. And clustering deals with finding clusters, where clusters are a group of objects in the dataset, group of points, that are similar to each other. As you can see in the screen with a red dashed line, show two different clusters in our dataset. While the utility of supervised learning might be more immediate for many, as for example you might train a model that is able to predict a quantity, and this model can be applied for yet unknown materials, and this could help addressing research and understanding what could be novel materials. For unsupervised learning it might be less immediate, the utility of this method. But let's see what are some of the applications of clustering, more specifically, to the different sciences. Let's start with the smallest scales in particle physics. In particle physics, when you are in colliders, particle collides at extremely high energy. This produces these collisions, many different particles, and a huge amount of information. And this information is treated with clustering. You can use clustering is used also in material science. One example is that it can be used for benchmarking. You have a very large data set, and you might want to find within that data set what are the most the best prototypes that can be used for benchmarking, and this can be done with clustering, finding such prototypes. It is used also in biophysics, so when you're attempting to simulate the dynamics of biological systems using molecular simulations, you find that biological systems live in metastable states and constantly fluctuate, oscillate between these metastable states. Clustering is used to identify metastable states and group together all those configurations that belong to the same metastable state. Well, it is also clearly used also in astrophysics, because you are dealing with a huge number of different objects as stars and galaxies, and you might want to use some automatic method for dealing with all these objects and structure your unordered data. As you can see already, applications of clustering are essentially on all scales of sciences, and it goes beyond also on very or more abstract fields, as in graph theory, and some applications of clustering graph theory may be for many the most obvious applications, which is on social networks, for example. Clustering is used to find users, individuals, which behave in a similar manner. Clustering is also used in more applied engineeristic fields, as in image compression. You have a very high resolution picture, and you might want to make some image compression, and clustering can be used for this purpose. At this point, we see that clustering is used in many different fields with extremely different applications. So now you might ask, what are good or bad clustering algorithms? And is there any clustering algorithm that outperforms all the others? So we should just learn that kind of algorithm and using it for all our applications. So now let's see how this works. Well, firstly, the first question that we should answer before understanding if an algorithm is good or bad is clusters are good or bad. So what I mean, how can we define if a cluster is well defined or not? If the clustering that we found is what is required for our application. In this lecture, I will work with two-dimensional data. The reason is that it is instructive to see how clustering works in all these steps, and also because the human intelligence is very good at finding clusters on a two-dimensional plane. So we can immediately assess whether our clustering algorithm has worked well or not. And I believe that all of you here is able to detect three different clusters, which are the ones that have been now shown. Now we would like to judge these clusters and understand what are the characteristics, the properties that a cluster should have. And we can define good clusters if clusters are separable and compact, as in this case. So we want that each cluster should be well separated, well distant between all the other clusters, and groups within the cluster should be similar to each other. What we want is that objects within a cluster would be all very similar and all quite different from objects from other clusters. And in this case, I would say this works quite well. Clusters are separable and compact. But now we might want to see on a different example if this is still true or not. So let's see this data set here and and try to guess what is the best clustering algorithm, the best clustering in this case. Well, let's start with the two qualities. We are looking for separability and compactness. If you're looking for separability, the best clustering, I believe, is this one. So we have three clusters, and we have a large cluster on the top and two small clusters in the bottom. They are separable because we see dense points, and there are regions, empty regions, where there's no points that separate all the different clusters, in our case, the three clusters, from the top and the bottom. But if we ask for compactness, this is maybe not the best algorithm. This is not the best partition of the space. And the reason is that on top, the larger cluster, if we take point at the extreme left and we take point at the extreme right, they are quite distant. They are much farther away than points that belong to the different clusters in the bottom. So I would say that in this case, clusters are not compact, are lacking some compactness. If we require our clusters to be compact, the partition of the space could be, the best partition could be another one. The one that we see with the green lines. So on top, we have the larger cluster divided into two different clusters, and the two smaller clusters in the bottom are merged into a unique cluster. This is definitely more compact than previous partition. But, on the other hand, this is definitely not separable, especially if we look at the two clusters in the bottom, the one that came from the larger cluster. There is a green line that separates the partition and points close to the green line. The reason why it should belong to one or the other cluster is not very clear. This seems quite arbitrary. We cannot really justify well. There's not any empty space between the two clusters. This example is to show how difficult it is to assess a good quality of a cluster, and this very depends on your application. And then we will see during this lecture that there are different algorithms that do something better than others. I won't discuss much about the quality of cluster. There are many possible. This is not only about separability and compactness. There are many indexes, internal indexes, external indexes, and if you are really interested in this topic, I really recommend you to watch the video that you can now see on the screen. During this lecture, I will mainly focus on three types of clustering algorithm: partitioning clustering, agglomerative hierarchical clustering, and density-based clustering. I will start with partitioning clustering, and more specifically with kmeans. This is the most exemplary algorithm regarding partitioning clustering, and this is also one of the most famous algorithms. There are many reasons that we will see. And the point is, it is also very old algorithm, but still valid and still very much used. So let's see how k-means works. I'm just drawn this data set. There are some points that are on that you can see, and now we would like to group these points and we simulate how k-means would work. So this is a whole work that I've done by guessing, by hand. So don't expect like certain position that we will see might not be exact, but we can still have a qualitative assessment of how this algorithm works. The first thing that k-means does is to extract two random positions that are our centroid position. Now you can see this red cross. Once the centroid position have been extracted, have been found, the algorithm associates to each of the centroids the closest particle, as it is here. Now, something very important about k-means that I didn't mention. The k in the name is the number of clusters that we are looking for. So this is a very central part of k-means. We have to determine before what are the clusters that we are looking for. In this case, we can look at the dataset and then we can already see before that we would have two clusters. And that's why we put k equals 2. And when we put k equals 2, the algorithm starts generating two random positions that are the two crosses. And now we have indeed these two clusters, and each of the cluster contains 5 points. Once we have found the first iteration of clusters, the algorithm is going to recompute the centroid position. So we can see this is where it would compute the position. That is the average of all the particles that are within the cluster. And from this new position, we would make a new assignment, a new grouping, and this is what we would obtain. So in this case, the number of particles has changed. Now we have 4 particles in the left cluster, and we have 6 particles in the right cluster. Again, now the algorithm is going to compute the position of the centroid, and this position now is going to be the average of the 4 particles to the left cluster and the average of the 6 cluster particles in the cluster to the right. And if we have this new partition, we would again see 4 particles in the left cluster and 6 to the right. This means that the number of particles in each clustering did not change. And if it does not change, the centroid position does not change, and the algorithm has converged. We found this clustering, and this is exactly what we would have guessed in the very beginning if we had to find the clusters just by looking at the dataset. But now we would like to see how this algorithm performs on, this is the position of the new clusters indeed, and then now we would like to see how the algorithm would perform on a, let's say, real data set, still artificial, something that I have generated, but we would use some Python packages to find the clustering in a more quantitative way, not just qualitative. Now, all these plots that you're going to see, all these data sets and all the partitioning that you will see throughout the lesson, is something that you can also reproduce yourself by going into the AI toolkit. You will find a notebook that reproduces these results, and you can play around with it, and I really encourage to reproduce what we have discussed and trying maybe to change the parameters and see what happens and explore the different combinations, or even trying different algorithms that I won't have time to mention during this lecture on your own on the same dataset. So now we begin with this very simple dataset that are 4 blobs using the sklearn package. That's how this dataset is produced. And we fix k equals 4, and this is what the algorithm would find. Each color represents a different cluster. This is something that will appear for all the next plots, so one color, one cluster. And the 4 clusters that we have found, I would say, are the ones that we would expect to see. I guess that most of you have, probably all of you, have already thought that those are the 4 clusters that the algorithm would find. And this is the most natural partition of the dataset, I would say. But now, if we change the value of OK, what happens? And this is a very important question. And the reason is that when you're applying clustering to unknown dataset, you might not know in advance what are the clusters that you're looking for. This is something that you should explore on the dataset. There are applications where you desire a fixed amount of clusters, and those applications kmeans is wonderful. But otherwise, you might have to explore the number of clusters. So let's see firstly what happens if we increase k, if we ask to find a larger number of clusters. This is what happens when k is equal to 7. We would find that the cluster, the larger blob, all to the right, is divided into 4 different clusters. Well, we said in the very beginning that we desire clusters to be separable. And this clustering is certainly not separable, is lacking separability. There's no reason why the blob to the right is divided into 4 clusters, especially because all those points were extracted from the same Gaussian. So this partition looks extremely arbitrary. We can say that we are not very satisfied with this result. But then let's see what happens if we divide the space into 2 partitions. So if we insert k equals 2. In this case, we have, I would say, a reasonable partition. We have the larger cluster that is left by itself, and the 3 smaller clusters that are all merged into a unique cluster. So if the question is, we have an unknown data set, and we might want to have 0, 1, a point we just want to separate into 2 different parts our data set, this could work. This could be a good partition. It is a meaningful partition. And comparing it, the 2 partitions, with k equals 2 and k equals 4, well, I would still say that the k equals 4 is a better partition, also because I know the dataset was generated from 4 Gaussians, so this is simple. But also k equals 2 somehow makes sense. And also another question is, we can see why those 3 clusters, so the questions whether those 3 clusters should be together or not, it is a reasonable question. And this is something that we will see also at a later stage in the second part of the lecture on another algorithm. So really keep this in mind. This is a good question. This is a point. So how can we decide what are the clusters here? There are methods that I'm not going to mention as the album method. I'm not going to describe in detail. But this is at least something that we should consider. And for sure, I would keep in mind that these two partitions are still both reasonable. But now we would like, indeed, we see that we have this, we have to insert this value k in our algorithm. And now we move on the next class of methods that what it's doing is essentially trying to give this multi-scale, this different resolution of clustering. This is hierarchical clustering. More specifically, I will describe agglomerative hierarchical clustering, and I will start with the VARD method, that is a linkage method. Now, I will explain you step by step what this means and how it works. With the VARD algorithm, well, when we have agglomerative clustering, it works. So let's first start with the basis of agglomerative clustering. Again, we have here this data set and an artificial data set for having a qualitative description of the behavior of our algorithm. And what an agglomerative clustering does is to initially place all points in its own cluster. So this is the initial situation. So here we have 5 points, and each point belongs into its own cluster. Then agglomerative clustering does the following. It merges the closest pairs of cluster until all clusters, all points are merged into a unique giant supercluster. And the question now is how to determine what is the closest cluster in this case. And this is where the VARD algorithm is useful. So we would like to the VARD algorithm determines how these distances are computed. And what it says is that the distance between two different clusters is given by the difference on how much the internal distance of the cluster would increase after merging. Okay, so now this might seem complicated, but it's not. So let's try to understand what this means. The internal distance of a cluster is how much each point is distant from the center. So you can think about it as variance. And variance is in fact, and this is something that like a compact cluster has. So a compact cluster has is minimizing the internal distance. So when you have this internal distance and then you merge in two clusters into a unique cluster, from two centers you pass to only one center. This means that necessarily internal distance has to increase. So when we merge two clusters into a unique cluster, internal distance increases. And the difference, how much it increases from the two into a unique, it is the VARD distance. So we see that the VARD algorithm is trying to make clusters compact. It's trying to minimize the internal distance of clusters. So in this case, it will merge the two clusters to the left into, as you can see now here. And the next step would be to avoid, it doesn't like this algorithm doesn't prevent the growth of huge clusters, because this is something that is going necessarily to increase the internal distance. Let's say it is a conservative, has a conservative approach regarding the size of the clusters. And in this case, in fact, the best solution would be for the algorithm to merge the clusters to the right, rather than making the other cluster increase from 2 into 3 components. And then it would assign the single point to another cluster, and then the final result is the following, where all points are within a unique large cluster. Clearly, we are not interested in this result, so the final result of the algorithm is not the most interesting part, because it simply assigns all points to one cluster. But what we are interested in is how the algorithm varies for different levels. So we would like to see how it behaves. So we would like to see how the different clusters are merged into each other. What are the interconnected dependencies of all clusters? And for doing so, we have a dendrogram. That is the most characteristic thing of the VARD algorithm, of the hierarchical algorithms. In the dendrogram, we see on the y-axis the distance, and this simply says when the algorithm stops, the distance where the algorithm should stop. The point is that when we have done this agglomerative clustering, the distance at each iteration always increases. The cost of merging increases. And at a certain point, we might say, stop the algorithm, stop merging when the distance reach a specific value. And this is what the distance means. The different branches are the different clusters, and the x-axis you can see the points for each cluster. Now, this dendrogram, I stopped at a certain distance, even if you can see by default a 0 on the y-axis, it does not really arrive at 0. So at a certain point, it just stops merging here, the dendrogram. Otherwise, you would see a total of 1,000 different points, different small branches in the bottom, because then it would have one cluster for one point. And this is something that is not very, that we cannot really analyze well. So we stop with a certain distance, showing how the dendrogram behaves. And now we are interested in exploring how the dendrogram partitions space. We have, for example, that if we select a distance equals to 4, we have 4 clusters. This is, and in fact, if we look at this line and we see how it cuts all the different branches of the dendrogram, we see it cuts 4 different branches, and those are the 4 clusters that we can see to the right. And this is exactly the kmeans results that we've seen before. But what this algorithm gives, more than kmeans, is that we can explore different levels. So now we can see what happens at 100. At 100 we find this partition. And here we gain the information that the 2 clusters in the center are more connected than the one all to the left. And then we can later finally increase the distance to 200, and then we find again another result of k-means for k equals 2. As you can see, the dendrogram, this is the most interesting part of this, this algorithm, also because it allows to explore how it is structured, so how the clusters merge, so the interconnection with the cluster. But here still remains unanswered the question, so what is the best partition between these 3 all together as here, or just having like 3 different ones, or just keeping having 3 clusters with the 2 in the middle merged together? This is something that again I will show you in the very end. There is an algorithm that attempts solving this question. Well, now as you can see, the results here they were essentially the same as k-means. In fact, k-means and the VARD algorithm are essentially trying to minimize the same cost function. They are trying to build clusters that are compact. And in this case, you can see they succeed. They found the clusters in the right way, unless you ask for more than 4 clusters. But the reason is also that this dataset is quite simple. We have 4 blobs, and blobs are quite spherical, and they are very simple for an algorithm that is attempting to find these compact clusters. It's very easy to identify these clusters, also because they are very separable. That's an easy task. So now let's challenge these algorithms with a different dataset. Let's try this dataset here. So now again we have the same as before, so the 4 blobs that we have seen before, but in addition we can see 2 more clusters to the bottom right. Those are 2 moons, half moons, which is also another function for scalar. And this is ideal for testing algorithms that are not relying on finding compact clusters. And in fact, if we then apply the VARD algorithm and we stop when it finds 6 clusters, we can see that it's essentially failing in detecting the regular shape. So the 2 half moons are not well separated. Again, if we are looking for separability, this is not separable. Those clusters are absolutely not separable, because when you're passing from the green to the yellow parts of the half moon, it's really easy, really difficult to justify why there is such transition, and this point looks extremely arbitrary. And if we do the same with kmeans, we obtain again the same results or similar results, testifying again the fact that VARD and kmeans are very similar. And this is also another, you can see it also here. So now the point is there are many applications where you might just desire compact clusters. In those cases, kmeans and VARD are optimal. But you have also many other applications where there might be clusters, irregular clusters. So you might have clusters with different sizes, you might have with different shapes, and you would like to detect those clusters. So let's see how we can do this. So we should definitely find a different cost function, let's call it. So different targets that we aim to optimize. We cannot only search for compactness as these algorithms do. Let's still stay within hierarchical clustering, but we discuss now another linkage criterion, that is the single linkage, that is quite different from the VARD criterion, and we can see how this behaves on this dataset. But firstly, we can see from this dataset how it works. We have again the same 5 particles as before that we have seen with the VARD algorithm, but now we see how the single linkage criterion would work, would merge all particles. The first pairing is the same as the VARD algorithm, so we have the 2 points. I am calling sometimes points, sometimes particles, but I mean always the same concept. You can see those 2 points that are merged into a unique cluster. But then now the 2 algorithms, the 2 linkage criterion, are going to diverge, are going to do different things. So now the single linkage algorithm would merge into this other, would make the already big cluster into something bigger. And the reason is that the single linkage algorithm is not looking for compactness. It is simply assuming that the distance between clusters is given by the minimum possible distance among all possible pairs of clusters. And doing so, what happens is that if you have a large cluster, it is more likely that this is going to be closer to other points, And this facilitates a rich get richer dynamics. So big clusters tend to become even bigger. Big clusters are more likely to merge because they have many connections, they have many points, it is more likely that they have points close to each other. And again, here we can see that it rather finds one cluster that iteratively grows this single linkage algorithm until finding again the same results as all agglomerative clustering, where that it finds all points within one huge supercluster. But if we then apply now this algorithm to our previous dataset, and we select a distance of 1.03, this is what we would find. We can find our clustering, and we can find that the two half moons are into two different clusters, as we would expect. So this algorithm is able, it succeeds to find different shapes. Also because it does not have any constraint on the compactness. It's not trying to make compact clusters, so it lets clusters grow in any direction, as long as there are points close to each other. But if we look at these results a bit more carefully, we might see something that we don't necessarily like. We might see those 2 points, and those 2 points do not belong to any cluster. They have their own cluster. And as I said, we pretend to be able to understand how clusters are, right? So, and we can, by looking at it, we can easily guess that those points, in the end, they are not single cluster. They rather belong to the larger blobs that are next to them. But they are too far, considering the cutting threshold of 1.03. So the distance from the other points is somehow is larger. To solve this problem, the most trivial solution that we might have is to simply increase the value of the distance, of the threshold distance. So here we have 1.03, and we increase this value, and let's see what happens. We pass to 1.04, and the two blobs in the center have merged. And what is worse is that the two single points are still within their own single cluster. You can see they have different colors still. And this is an example of the get richer behavior of this single linkage algorithm. So it facilitates the growth of large clusters. And again, these results, the one to the left especially, I wouldn't be very satisfied. And what is even worse, I would say, is that imagine if you're working with noisy data. Imagine if you have such a data set. So now we have the same data set as before, but I've just added some, I've included some random points over this plane. And they represent noise or outliers. So now I would just like to open briefly a parenthesis and just saying that noise and outliers, I will use these words with the same meaning essentially, even though they might sound extremely different, because noise is some noise that comes from your equipment, so you might fail to detect correctly some observable, while outliers are regular objects that are simply not classified into any cluster. They are just different, just very different from all the others. But for us, this doesn't change much for our clustering algorithm. So we can say noise or outliers, at least in this purpose, regardless of the source of the position of those points. So now let's come back on our single linkage algorithm and let's see how it performs on this dataset. And as you might have already guessed, it fails to to detect the noise, because there is no any noise detection I haven't described, and is connecting the larger clusters. That is again what noise would do for this kind of algorithm. So would just act as bridge between the different clusters. So now I would move into the next step, which are the density-based clustering. But before moving to the next topic, I think it's a good time to stop and taking questions. Thank you for your time.